These are notes for section 10.1, Math 75. Okay, so we're learning something called relative maxima and minima. That's the plural of maximum and minimum. One maximum, two maxima, one minimum, two minima. So we take this graph here. It's on page 631, it looks like. Okay, this is called a relative maximum. This is called a relative minimum. Okay, so relatively speaking, in a small neighborhood of this point, it's the highest point, so it's a maximum. In a small neighborhood of this point, it's a minimum. Now, there might be points on the graph that are lower, but relatively speaking, in a small region of this point, it's the lowest. Likewise, there might be other points on the graph that's higher than a maximum, but relatively speaking, on a small neighborhood, that's considered a maximum. Okay, and we have this property for increasing and decreasing functions. Okay, so remember that derivative gives me slope. And think back to your algebra. If the slope was positive, it looks like this, the function's increasing. If the slope is negative, it looks like that, the function's decreasing. And we're always moving from left to right in our frame of reference. Okay, so if f prime of x is greater than 0, then f is increasing. This means slope positive. F prime of x is less than 0 means the function is decreasing. Okay, and for relative maximum and minimum points, okay, the derivative will either be 0 or it's undefined. In practical terms, we're almost never going to tackle any situation where the derivative is undefined, but we'll be taking a derivative and setting it equal to 0. Okay, so if you take a look at this picture here, this happens a lot for us. Relative maximum looks like the slope is 0. Relative minimum, slope is 0. This is a relative maximum, but there's no derivative here. This is not differentiable at this particular point. We have a corner point. Okay, but in actuality, for the problems that we will do, that almost never happens. All right, so on page 632 now. Okay, this looks like a relative maximum. Okay, here the derivative is 0. Derivative is undefined. It's called a critical point. Critical point is a point where the derivative is either 0 or undefined. For us, again, most of the time it'll be derivative equal to 0. Okay, what's true about a maximum? Well, if I come from the left, the function's increasing, slope is positive. And if I move a little bit to the right, the function's decreasing. Okay, that's what makes this a relative maximum. How about a relative minimum? Like this. Well, if I move a little bit to the left, the function's decreasing. And if I move a little bit to the right, the function's increasing. So that's what categorizes a relative minimum point. Okay. So if you take this picture right here, okay, this is a relative maximum because on the left side it's increasing, the right side is decreasing. Okay, think of a ride, like a roller coaster ride, right? You go up and then you go down until you reach the maximum. That looks like a minimum because to the left of it you're going down, and to the right of it you're going up. So that's what makes this point a minimum point. And again, the plural, maxima and minima, that's plural of maximum. One maximum, two maxima, one minimum, two minima, minimum point, maximum point. Okay, now, it's possible that you have a slope of 0, but you have neither a maximum nor a minimum, like this. Okay, the text calls that a horizontal point of inflection. We'll talk more about horizontal points of inflection in the next lecture. Okay, but horizontal point of inflection for this one, the function's increasing, slope of 0, and then it still increases. Okay, so the abbreviation is HPI, horizontal point of inflection. Okay, you go up, and then you still go up. It could also be you go down, and then you still go down. That would be something called a horizontal point of inflection. Okay. All right, so we're going to try some of the problems now on the homework. Okay, so you can see some of the problems here, 7 through 10. On page 640, okay, and then there's some more at the bottom, 15 through 20, 25 to 30. All right, so I'll be doing these problems now. Number 8, y equals x cubed minus 3x squared plus 6x plus 1. Now the usual protocol is to set the derivative equal to 0. So first take the derivative, 3x squared minus 6x plus 6, set it equal to 0. Factor out the 3, x squared minus 2x plus 2 equals 0. This one you can't factor, so use a quadratic formula. So A is 1, B is -2, C is 2. Throw it in the quadratic formula. X is negative B plus or minus the square root of B squared, 4, minus 4AC, 4 times 1 times 2, over 2A. But this can't happen because that gives me 4 minus 8, which is a negative. I'll be taking the square root of a negative, and we can't have that. Okay, so there are no critical points. Okay, so that means this graph, whatever it looks like, has no maxima or minima. In fact, the whole graph will do the same thing, either increase or decrease. Okay, what you can do is just plug in a nice number like 0. Y prime of 0, you get 0 minus 0 plus 6 is 6. That's positive. That means the function's always increasing. This is my abbreviation for increasing. As I move from left to right, it's going up. So the function's increasing on negative infinity to infinity, which means all real numbers, and the function's decreasing nowhere. And so for the first example, we just have an instance where we have no critical points, no maxima or minima. The function's always increasing. Okay, let's try number 10. Y equals 15x cubed minus x to the 5th plus 7. So take the derivative, 45x squared minus 5x to the 4th, set it equal to 0. Factor out of 5x squared, then 9 minus x squared equals 0. This factors into 3 plus x, 3 minus x. Okay, so my critical numbers are whatever makes the derivative 0. That would be x equals 0, negative 3, and 3. And then after that, I do a sign chart to determine where the function's increasing or decreasing. But at 0, negative 3, and 3, the derivative is 0. That means I have a horizontal tangent. So I might have a maximum or minimum. Okay, so I draw on my number line, negative 3, 0, and 3. Pretend the red's not there. I have to come up with the red. So at the moment, it looks just like that. Right, and then I pick something in each region. So something over here would be like negative 4. Something in here would be negative 1. Something in here is 1. And something here is 4. Okay, and I plug into this expression for the derivative. Okay, but notice 5x squared is always positive. Right? If I plug in a positive or a negative quantity, the 5x squared is going to be positive. So that's all of these pluses indicate the 5x squared. So I just have to look at these two. Plug in negative 4. 3 plus a negative 4 is negative. 3 minus a negative 4, that's like 3 plus 4, positive. So a positive times a negative times a positive is a negative, so I put a minus sign there. Plug in negative 1, I already know that's positive. 3 plus a negative 1, positive. 3 minus a negative 1 is still positive. Positive times positive times positive is positive, so positive. Plug in 1, we already know this is positive. 3 plus 1, positive. 3 minus 1, positive. They're all positive, so once again, positive. Then I plug in 4. I already know this is positive. 3 plus 4, positive. 3 minus 4 is negative. So if I multiply a positive times a negative, it comes out to be a negative. So my sign chart is minus, plus, plus, minus. Okay, so if the derivative is negative, like these two, the function's decreasing. I'm going down the ride. I'm going down the roller coaster. These two places, the function's increasing. It's going up. All right, so at negative 3, the graph goes down and then up. That's a minimum, relative minimum. At 0, it goes up and then it still goes up. That's neither a maximum nor a minimum. That's going to be a horizontal point of inflection, HPI. And then at x equals 3, the graph goes up and then it goes down. So that makes it a relative maximum. Okay, 16, I'll do in more detail. Y equals x squared plus 4x. Now, you might recall from your algebra that that looks like a parabola opening upward. Okay, and that's verified by our final answer, but we'll get to that. Okay, so take the derivative. The derivative is 2x plus 4. Set it equal to 0. Subtract 4. 2x equals negative 4. Divide by negative 2. Divide by 2. X is equal to negative 2. So that's a critical number. Okay, let's actually find the y coordinate this time. So f of negative 2, put negative 2 here and here. You have negative 2 squared plus 4 times negative 2. 4 minus 8 is negative 4. So the ordered pair is negative 2, negative 4. All right, so y prime was 2x plus 4. I lay down negative 2. Pick something over here, something over here. So something to the left of negative 2 is negative 3. Plug in negative 3. 2 times negative 3 plus 4. That's negative 6 plus 4. That's a negative quantity. Something to the right of negative 2 is 0. 2 times 0 plus 4 is positive. Okay, so negative derivative means decreasing. Positive derivative means increasing. So that makes this a minimum point. It goes down, then goes up. Okay, so these are intervals of increase and decrease. The function's decreasing from negative infinity to negative 2, and it's increasing from negative 2 to infinity. So that means negative 2, negative 4 is a relative minimum. It turns out also to be an absolute minimum. We can talk next time more about an absolute minimum. It's absolutely the lowest point. How do I know that? Because all the graph does is it goes down and then it goes up. So there we go. It goes down and then up, and that's all it does. So that's our minimum. Okay, 26. Y equals 1/4 x to the 4th minus 2/3 x cubed plus 1/2 x squared minus 2. Okay, so the derivative actually comes out nice. 4 times 1/4 is 1, so I have x cubed. 3 times negative 2/3 is negative 2 x squared. 2 times 1/2 is 1, so plus x equals 0. Factor out the x. X squared minus 2x plus 1 equals 0. This factors into x times x minus 1 squared. Okay, so what makes this 0? 0. What makes this 0? 1. So those are my critical numbers. Okay, let's find the actual y coordinates. F of 0 is negative 2. Look at 0 there, 0, 0, 0 minus 0 plus 0 minus 2 is negative 2. F of 1, unfortunately, is a lot worse. Put a 1 here, 1 here, 1 here. Well, at least 1 to the 4th power is 1. 1 cubed is 1. 1 squared is 1. So I have 1/4 minus 2/3 plus 1/2 minus 2, which is 2 over 1. Common denominator is 12. So in red, I multiplied by the appropriate number to get a denominator of 12. So 4, I need 3 over 3. 3 needs 4 over 4. 2 needs 6 over 6. 2 over 1 multiplied by 12 over 12. Okay, so that gives me 3 minus 8 plus 6 minus 24. That comes out to be negative 23 over 12. So 1 comma negative 23 over 12. Okay, then I do my sign chart. So I lay down 0 and 1. I lay down on my number line the critical numbers, the values where the derivative was 0. Then I pick something over here, negative 1. Pick something in the middle, 0.5. Something over here, 2. I plug in, but again, I notice that I have blah, blah, blah squared. Once I see something squared, it's automatically positive. So positive, positive, positive automatically because of this. So the sign is completely determined by x. So negative 1 is certainly negative. 0.5 is positive, and 2 is positive. So negative times a positive is a negative, and these two are positive. So decreasing, increasing, increasing. Okay. So what does that mean about at x equals 0? Goes down, goes up, minimum. How about here? It goes up, and it still goes up. That's neither a maximum nor a minimum. That's a horizontal point of inflection, HPI, you have there. So 1 comma negative 23 over 12 is a horizontal point of inflection. Okay, so the function's decreasing from negative infinity to 0, and the function's increasing between 0 and 1, and also between 1 and infinity. Then you might say, why don't you just go from 0 to infinity? Technically, right at x equals 1, the function is not increasing. It has a slope of 0 ever so slightly, and then it goes back up. Right, so here's the picture. Goes down to a minimum, 0, negative 2. Goes up to 1 comma negative 23 over 12. Just for a split second has a slope of 0, and then it goes back up again based on this. Okay. Okay, then one more like this, 28. C of x, C evidently could stand for cos. X cubed minus 3/2 x squared minus 18x plus 5. So the derivative is 3x squared minus 3x minus 18. Factor out of 3, x squared minus x minus 6. Factor further, 3 times x minus 3, x minus 2. That's a funny looking parenthesis. Set it equal to 0. Okay. Well, that can't be 0. What makes this 0? 3. What makes this 0? Negative 2. Okay. To find a y coordinate, plug back into the original. So put a 3 here, 3 here, 3 here. 3 cubed minus 3/2, 3 squared minus 18 times 3 plus 5. punch it in your calculator, negative 35.5. So 3 comma negative 35.5. Same thing for negative 2. Put a negative 2 here, here, here. Negative 2 cubed minus 3 halves, negative 2 squared minus 18 times negative 2 plus 5. Grind it out, it's 27. So negative 2 comma 27. All right, then do my sign chart. I rewrite the derivative. C prime is 3 times x minus 3, x plus 2. So I lay down the critical numbers where the derivative becomes 0. So that's negative 2 and 3. Then I pick something over here, something in here, something here. So over here would be like negative 3. In the middle, 0. Over here, 4. Plug in here. Well, 3 is always positive, so plus, plus, plus. These 3 pluses represent the 3. Plug in negative 3. Negative 3 minus 3, negative. Negative 3 plus 2, negative. Positive times a negative, positive. 0. 3 is positive. 0 minus 3 is negative. 0 plus 2 is positive. So I have 1 negative. That makes the whole thing negative. Finally, 4. Everything is positive. 3 is already positive. 4 minus 3, positive. 4 plus 2, positive. 3 positives multiplied together, positive. All right, increasing, decreasing, increasing. So if you go up and then you go down, this must be a maximum. Here you go down and then you go up. This must be a minimum. Okay, so here are intervals of increase and decrease. F is increasing here from negative infinity to negative 2, union 3 to infinity. And the function f is decreasing only between negative 2 and 3. And we said negative 2, 27 must be a maximum. 3 comma negative 35.5 must be a minimum. So here we go. Horizontal tangent, slope is 0. Slope is 0. Up, down, up. So you can see this is a maximum, and this must be a minimum. Okay, so these were the lecture notes, and I'll show you the quiz again. Some of you may not have gotten a quiz. Due Tuesday at our regular starting time of 5:40. Okay, determine any relative maximum or minimum values of f of x equals x cubed minus 3x squared. So do the techniques that we just discussed. Take the derivative, set it equal to 0, find the y coordinates, make a sign chart to determine if your points are maximum or minimum quantities. Okay, so determine any relative maximum or minimum values of f of x equals x cubed minus 3x squared. All right, so these are notes for Milham's Math 75 for section 10.1.